Okay, so today I will present you our last results in the team, but let me start with some context. Okay, fine. So one of the main aims of my team in Marseille is on the characterization of the dynamics of cortical folding that is illustrated here. So basically from the very beginning to, well, potentially the end of brain maturation. And so concretely, one of our main aims is to estimate this kind of normative curves, such as you have in your carnet de santé. I don't know how to translate that. And here, so more specifically, what we want is to understand how from this simple shape that is common to all humans at the very beginning of the gestation, we end up having very different folding pattern in adults. So I'm sure you have seen this kind of visualization from the work of the team of Jean-François Margin, of course. And here, what we want is to characterize quantitatively what is illustrated here with this pink arrows. That is the emergence of the variability across individuals in the shape of the cortex. Okay, so many fundamental questions, of course, and also, as usual, in this kind of studies or topic, of course, we also have potential clinical applications if we are able to characterize normal brain maturation. Then, at the same time, eventually, we can identify new biomarkers of potential abnormal brain development. Okay, so to do that, we need lots of data. So there is this paper by Bozek and colleagues that did assess quantitatively, for instance, the impact of sample size, not only on the average trajectory, but also on the estimate of the confidence interval and centiles. And so we know that we need thousands of data points. So here, thousands of MRIs, and including large part of the period that we are interested in is before birth. Okay, so here we need thousands of fetal brain MRI. That's the first thing that we need. The other thing that we need is precious team of collaborators. So here, that's my pleasure to acknowledge the work of these colleagues. So the three other guys from the MECA team in Marseille, permanent researchers. Close collaborator is François Rousseau from Brest, who is an expert in fetal MRI processing, deep learning. The PhD student and postdoc. We have actually several engineers who did contribute here. And on the right, you see 4 medical doctors who were really instrumental. I mean, without their very concrete time and implication, nothing of what I will show would be possible. Okay, so the plan of today. So by the way, I did it a bit short, especially to keep some time for discussion with you. So do not hesitate to interrupt me if something is not clear. So first, I will explain you how we did build a very large data set of fetal MRI acquired in clinical routine. Then what we need to process the data and extract these kind of objects. And then I will go I will give a recap of the first, I would say, interesting results that we got. It has been published. You have the link in the abstract of the talk of today. I did provide the link to the paper that got published very recently. And I would like to show you some perspectives. So I hope I will have time to show it. So the first serious load of work that we did achieve was this, to retrospectively access, manage, process all the fetal cerebral MRI that have been acquired in Marseille since 2008. So I've been working on that since 20 years now. And the aim is to get access to the MRI, neuroimaging data, but also clinical data. Of course, here, I mean, by definition, this kind of images have been acquired because there is suspicion of an abnormality, but also phenotype. So for instance, just knowing the sex of the fetus is not trivial, especially it's not, you cannot access that on cerebral MRI. Okay, so here you need to access other kind of data that are not stored on the same system. Well, so you know all the complexity. And also, of course, there are many constraints to legal and regulatory aspect that we did achieve also well. So the key ingredient here is this interaction that we need to implement between the three units, three departments of the hospital: neuroradiology, but also pediatric neurology and obstetrics. And we need all these departments to discuss in order to really understand what's happening during the pregnancy, and not only whether the MRI is normal or not, but also whether the pregnancy is going well, because you could, I mean, and it's happened actually often that the MRI is completely normal, but for some other reasons there is a problem, and so we cannot consider this image as a control. And very briefly, another challenge that we are currently addressing in Marseille is the assessment of the postnatal development. Okay, so here this started 1 year ago. We got funding. We called back all the families from all the fetuses that were scanned and had normal MRI to really assess the development after birth. So now we have 200 families that have been contacted, and we have the violin for 80 subjects so far. It's ongoing, and you see we will do that at the multicentric level with the CHU Necker and Montpellier. Okay, so today, this is the current status of the Marseille database. So we have, you see, a bit more than 2,500 cases. You see the validation. That's when the medical doctors have been checking the data. You see we are, well, like 300 or 400 to go. Then we have another round of validation with the imaging data. And then when we have everything, so you see we have everything for more than 200 cases, then we can eventually look more closer and start looking at subgroups. So we have more than 500 cases with normal MRI and also normal pregnancy on that. We have 400 cases with, I mean, complex pathology, genetics, hemorrhage, all this kind of data that are very complex and that we will not use, at least in short term. And then we already have some other subpopulation of interest. For instance, so here it's not corpus callosum agenesis, but corpus callosum anomaly. So more than 200 cases. And for instance, almost 200 cases with ventricular enlargement. That is, I think, very interesting. And we have, of course, lots of other subpopulations like these are multiple pregnancy. And here it's like 60 fetuses with intrauterine growth restriction. When we compare with the state of the art, we have here a really nice database with, I mean, lots of information that I think will be of great interest for many years, I hope so. So we have access to other kind of data. So for instance, the sex, as I said, it's not systematic. So we have, you see 65 cases for which we don't know the sex for the controls. For some subgroups, we did not invest time, so we did not even try to get this data. But you see for the controls, for the corpus callosum anomaly, and for these three groups, you see that we can get interesting data. We have much more than that. For instance, the birth weight, well, okay, many information that will be of interest in the future. To me, what is important is that with this kind of data, you have access to the heterogeneity that you face when you use data that has been acquired in clinical routine. And here, actually, with this implication of medical doctors, you can start having access to subpopulations. So for instance, in the subject with corpus callosum anomaly, actually, we can already identify subpopulations. So those for which the corpus callosum anomaly is isolated, there is nothing else in the MRI. The interruption or in corpus callosum anomaly, you can have corpus callosum agenesis. So part of the corpus callosum is absent, or even the corpus callosum can be entirely absent. So we have all these complex subpopulations. And for the ventricle enlargements, this is very interesting to me because there are a few papers, for instance, looking at the impact of the size of the ventricles on the shape of the cortex. And actually, what I did discover is that in our sample, with 200 cases, actually, for almost half of the cases, at birth, there is an transcranial echography. And actually, in half of the cases, the size of the ventricles has been back to normal by itself. So here there is, for instance, this is an illustration of the dynamics aspect of the brain development in utero, and I think it's largely unexplored. So with all this data, you see that I think we will have a lot of things to do in the future. Okay, now I will focus a bit on the imaging data to explain you why it's not trivial, of course. So first, I remind you that in fetuses, we do not acquire 3D volume because of the movement of the fetus. Okay, is moving continuously. So if you try to acquire a 3D MRI, there will be artifact related to movement, to motion. So we do not do that. What we do is that we acquire fast 2D slices that we aggregate along directions. Like we try to cover the brain along the sagittal, coronal, and axial axis. So we end up having like 3 or more stacks of 2D T2-weighted MRI. And so we did spend a lot of time and actually a lot of money developing this tool. So here, this is an open source pipeline that you can access. It's still under development, but now we are ready to welcome potential new users. And basically, from the stacks that you provide as input, the pipeline will automatically localize the brain, do this complex reconstruction that allows to estimate a 3D volume, high resolution volume from the stacks, and then segmentation and extraction of the cortical surface. That, in my work, is what I need as an input. Okay, just shortly, briefly, one example of methodological work that we did do to get the results that I will show later. So at the time we started this study, we were able to get the 3D reconstruction of like 150 subjects, but we did not have the segmentation. But we really need to dissociate the different tissues in these images. And well, this at that time it was an open question. And our approach was to start from postnatal, neonatal MRI, so the DHCP data that is public and for which they provide very good quality data because they have been acquired in research and with ground truth segmentation. And so here, without entering into the details, the idea is that we did train a model on the youngest neonatal subjects. We did predict on our fetuses, correct some of them, only a few, as you see, only 7 cases, and then fine-tune the model. And just with that, okay, sorry, we got this kind of results. So where we can dissociate the different tissues at starting from like 20, a bit before 25, to afterwards. Okay, and this we did apply that to now a larger cohort of subjects. So the DHCP, postnatal DHCP in blue, our subjects, so Marseille in, I don't know, purple, 150, and then at that time we had access now to the fetal DHCP, and also some preterm babies. Okay, so almost 1,000 MRIs. And for each of these MRI, have been able to extract this kind of objects. So this is a 2D surface representing the cortical interface between gray and white matter. Okay, so now we have that. We can start doing some research. And this now I will present you the main results. So when you have this kind of data, then you need to model the effect of age. So basically, you need to fit gross model. We did choose to use the classical normative modeling approach, Guillaume LSS, that has been introduced, for instance, in this paper. Now, these framework are very nice. Everything is well documented, so you can fit the different models to your data and see the importance and the benefit of fitting more complex models. So, for instance, here we have the lateral ventricles with very complex distribution, and you see that to fit a statistical model to this kind of complex data, we really need all the degrees of freedom that are available with this kind of method. So we did fit that to all the measures that we got from the segmented brains, segmented MRIs. So you see half postnatal, half fetal, fetuses in red and postnatal in blue. And you see these normative models, normative curves with the confidence interval for premature, white matter, deep premature. We have that for all the structures, so including now the surface area. Okay. And what you can observe here is what you would expect, I think, that well, from fetus to postnatal life, there is a nice transition. The evolution of the size of the brain and of the tissues is continuous. You see a bit of here an inflection, but mostly all these curves are really smooth, and the transition, the birth, does not seem to affect too much the development of the brain when you look at these kind of features. But now, what we did observe is this very different trajectory that we observe for one measure, that is the Gyrification index, but the ratio between the surface area and the area of the convex field that is illustrated here in green. So here, you see that clearly there is a gap, and so we did design a specific statistical methodology allowing us to actually assess statistically whether there is a gap, whether this can be demonstrated statistically. And yes, actually, with a method that is known as regression discontinuity design, we can measure statistically whether the gap here is significant. And here you see the log p-value and the effect size on the vertical axis, and you see that really this gap, actually, the statistics corresponding to the assessment of this gap is really specific to Gyrification index. So there, okay, there are for some structures, really the transition is very smooth. For some of them, it's a bit different, but really Gyrification is completely different. And if you measure this gap, size of this gap, and you compare to the increase in Gyrification during pregnancy, and during the whole pregnancy, what you observe is that actually this gap is as large as half of the increase in brain folding during fetal life. So this was really unexpected for us, but well, we need a lot of experiments in order to check that it was not an artifact from one of the many factors that you can imagine. And no, we think that this is real. And this was our first interesting result. There is another, let's say, structure for which the trajectory is complex, that is cerebrospinal fluid. So also there is here some part of the variance that is related to the size of the ventricles. And here you see also that there is something happening at birth. Okay, if you compute the RDD regression discontinuity design, you see that, okay, there is also a gap. And here you see that, especially the variance is reduced after birth. And actually, when you discuss with a neuroradiologist, like Gira, when I did show her this result, she told me, oh, yes, of course, that's expected, because when you compare a brain after birth, an MRI after birth, and an MRI before birth, of course, we expect to see this reduction in the external cerebrospinal fluid. Okay? And actually, our results suggest that with this reduction in liquid, we also have an increase in brain folds. So now, how can we interpret that? Well, here, to me, that's the main limitation of our study, okay, for many reasons, but we can still discuss what potential mechanism that could induce this increase in brain volume. So one possibility would be, right, we have mechanical constraints during the delivery. And here, I just want to showcase this crazy study. I don't know if you know this study. Olivier Ami, I think the obstetrician in the Lyon, I think. And here, what they did was to acquire MRI during labor. Okay, so here you see the same baby before the labor starts, and here during the labor. To me, that's the only study I know on this topic. It's quite impressive that it managed to do that. But in this study, they have been able to. It's quite impressive for the mother, not really for radiology. Yeah, no, I fully agree. But well, I think there was like 27 women who did accept to do this. So quite impressive. I think there are many limitations in this study, but basically they will split some models and observe this kind of change in brain shape. So, well, for sure, there is a very strong, strong mechanical constraints that are imposed to the brain of the baby during the delivery, for sure. Here, to me, this is something that we could test in the future, because there is data. We could, for instance, compare neonatal MRI between babies that were born with a vaginal delivery and compared to, for instance, the babies that were born with cesarean section. So this is something that we will test in the future. But there are also other possibilities. To me, well, my intuition is that the most important factor is really the drying of tissues. That would make sense when you see that with the increase in brain folding, you also have this reduction, drastic reduction in amount of liquid. And we know that just after birth, actually in a few hours from birth, there is this well-known loss in weight. Here, I've been looking at the literature. Actually, there are not that much data. We all know that a baby will lose weight after a few hours, but I did not find a study with a dynamic. So again, what we want is not only, okay, the loss, the weight loss is of this number. We would like really to see that how long does it take for the weight to decrease. I did not find that, but this is another option. Also, there are also many other physiological changes, like we know from animal studies that the composition of CSF changes between before and after birth. Of course, also there are massive changes for instance, in the blood circulation with birth. So there are many factors. Okay, so some of them we can investigate. Some will be much more challenging. And again, here I would be very happy to discuss with you if you have other suggestions. Another thing that we can do is to look locally at what's happening in the brain, because we did only here report global measurements, and I will show that in the perspective that we are on the way. Just an image for Jessica. We did also apply the same tools to the 100 preterms from the DHCP data. And here is the plot. So you see, basically, you see that, well, the preterm, they are really in the continuity of the neonates and maybe merge with the fetuses. Okay. And, well, there are many ways to interpret this. we have been arguing with the reviewers on, well, look, because at a given age, they are very similar. It means that what you observe here is just an effect of the acquisition of the MRI. I disagree with that, and we can discuss that further if we have time. But for now, I will move on, and eventually, if you have questions, I will come back to them. Okay, so now I just want to showcase a bit the new, very recent study we are actually running, just to again discuss with you the potential perspective and ideas. So one methodological aspect that I think is critical in brain MRI in general, but that is really critical in fetal MRI is the sensitivity of our measure to, data acquisition, processing, everything. Okay, so to address this question, we set up a collaboration with colleagues from Barcelona, Lausanne, and Zurich, and we also have access to the HCP public dataset. So here you see we did increase our sample size. We have more than 500 fetal MRI data. Also, in the meantime, we have this new tool that has been released that works quite well, not perfect, but really that's a very nice tool from Maria Deprez group that allows us to have an automatic segmentation that is more robust than what we did propose in our specific work. So what do we do with that? We have, as usual in multicentric studies, the question of the harmonization. Okay, so here what I show you is, well, the raw data for one given structure, a special structure. You will understand why in a few minutes. If you plot the data, so here we have it's work in progress. So here we are starting with 3 sites, and we will end up with 5 sites. And if you look at the volume of the cerebellum, the evolution of the volume of the cerebellum with age across the 3 sites, you see this: the green, the red, and, well, the blue. And if you use like harmonization techniques that have been published, like combat GAN, you observe that. Wonderful. Well, so if you go fast, you will say the conclusion will be, oh, very nice, this harmonization tool is so efficient. But when you deal with data that you have been manipulating since 4 years, you will have a look closer. And what you will observe is that for some cases, of course, everything is fine. They were already close to the average before harmonization. And for some cases that were clearly suspected to be outliers, the harmonization will manage to fit these crazy points in the confidence intervals. And when you do the QC, you see that actually for cerebellum, segmentation is crap. So basically, you don't want that. What you want is that either you manage data quality before doing the harmonization, or you want to understand and measure what is the impact of data quality on your normative curves. So this is basically what we are doing in a different way. So we did extensive visual assessment of the 500 cases. And so here, it's really preliminary results, but the idea is that we will somehow use this study to calibrate the QC. We have a continuous scale for the QC, and we'll assess what is the threshold that we need to impose on the QC to have a robust estimate, not only of the average trajectory, but also the centiles. Okay, here you see, for instance, the impact when you threshold, when you exclude more and more data, you see this is the 5/5 centile. You see how strong is the impact on this on the estimate of this centile, which is expected. Okay, but in the literature there is nothing about that, and we think that it's very important. And so, by the way, I showcase this other work that we did collaboratively. The tool is open. if you want to do some QC on fetal MRI data, please do not start from scratch. Please use this tool that we did develop. So it's just a Python tool. You install, you provide your stacks, and you will have this nice evaluation HTML page with you see different scores to be evaluated, and we provide a protocol, and we have been doing extensive assessment of the intra and inter-rater reliability. Okay, I have something like, I think, 10 minutes. Another perspective that was for David Germano, but please, Jessica and Lucy, well, he will see that maybe on the record of the talk. So, SPANG, Spectral Analysis of Gyrification, is a tool that has been developed by David Germano and Julien Lefebvre in our team. Very briefly, the idea that you decompose the curvature in different frequency bands, and you can then map here in each cortical region, at each point of the cortex, which band is dominant. So somehow you dissociate, it's a bit an oversimplification, but primary, secondary, and tertiary sulci that are illustrated. I will use this color map here because I use it after. In blue, like the larger, deeper primary sulci. In green, the secondary fold, and in red, the tertiary fold. And so in this study and the other studies from INDES, they have been using that on preterm babies. And here we are extending that to fetuses. So here you see just 4 examples of fetuses at different age with this decomposition. And with this decomposition, you can then assess quantitatively the evolution of this primary, secondary, and tertiary. So here, so on both plots, what I show is the Brown proportion. That is the proportion of the total power attributed to each frequency band. And I will start with this plot that is from this study by Jessica and Guillaume, where they did observe with preterm and full-term babies between 30 and 60 weeks, this evolution, so with like the primary fold that tend to lower in proportion, so there is no, the primary fetuses do not disappear, it's just that relatively to the secondary and tertiary folds, they tend to, the primary fold tend to decrease, meaning that just there is, on this period, a massive increase in the secondary and tertiary folds compared to the primary fold. And when, here that's very fresh results that we got last week. And here you see that, okay, if now we can eventually compare with what we observed between 20 and almost 40 weeks. And we see, well, basically I did look at this figure yesterday in the train for the first time. But what I can already observe is that the trajectory of before will probably be very close to what we have here. If you look between 30 and 40, so here, so like a decrease. And in parallel, an increase of the 2 others, and it's very visual, but I think that the major difference will be in B6, that I think will be lower than what you observe with preterm. That would be consistent with what we observe at the global scale with our Gyrification index. Another perspective, so this is another work. It's under review at TMI. The preprint is here. I will not enter into the technical details. If you have questions, I can go back to that during discussion. But what I want to illustrate here, it's more the results. You know, I will skip the methods. What I want to illustrate is that with this method we can compute 4D atlas. Okay, so 3D plus time. Okay, here you see that this atlas has been computed with control subjects. And what is important here is that with this method, you can combine control and abnormal brains in order to generate actually a 5D atlas. So 4D plus like we have an additional dimension that in this case will be rated to the size of the lateral ventricles. So you see here, this is the atlas we get with only controls. And then when we combine with a subset of fetuses with enlarged ventricles, then we have another dimension. We can generate an atlas with too small or too large ventricles. So basically, with the data, we learn these two. And with the method, actually, we can interpolate any size of the ventricles, including two small ventricles. That's well, it's more here for the illustration of the advantages of the method. What is important to me is that this kind of method is instrumental. We need that in order to process abnormal brains. Okay, and this is not trivial. So this is one brain with enlarged ventricles. If we take a normal atlas, you try to register a normal atlas at the same age, you have this kind of image with this kind of segmentation. So the registration-based technique, for instance, will have will actually fail to align both the cortex and the ventricles. So with this kind of method, you cannot get an accurate segmentation. And with this method, with this new method, actually, we can do much better. So this and this second illustration of the application to abnormal brains here, in this case, we combine controls with fetuses without corpus callosum, complete corpus callosum agenesis. And with that, again, we have for the atlas, so you don't see here, I show only one time step, but we have that for every time step between 20 and 40 weeks. What I want here to show is that with this, we have another cursor that is an interpolation between a normal brain and the brain without corpus callosum. And so this, for instance, has been interpolated without having provided any data with partial corpus callosum agenesis. And also another feature that to me is really interesting, that if you compare not only the size of the well, you see that the corpus callosum is absent. What you also observe is that the size of the ventricles is larger, and also the cortex is smoother. And this is completely expected. It's known in corpus callosum agenesis that the three features are combined. And when you interpolate, you actually have really an interpolation not only of the size of the corpus callosum, but also the size of the ventricles and the size of the smoothness of the cortex. And here also, it's just another view. And somehow, it's not really convincing, I think, here. But the idea is that we can interpolate subtypes of corpus callosum anomalies like hypoplasia. So to me, that's really important. Here, I think we are moving towards really the processing of abnormal brain, which is, of course, a real challenge. One of the last slides is just to showcase this other interesting study. Here, the PI is Olivier Coulon from the team in Marseille. And here, the aim is to acquire longitudinal MRI for fetus baboons, because here the aim is to have 10 time points per subject. The aim is to be able not only to estimate a trajectory that is an average across a group of subjects, but here really a different trajectory for different individuals. So here the aim will be to characterize the dynamics, eventually the variation across individuals in the dynamics, some maturing faster than others. And so this is a real challenge to acquire. So I encourage you to invite maybe Olivier next time. But the acquisition has been completed for 6 subjects, I think, with almost 10 time steps per subject. And we have T2 weighted MRI, but also high quality diffusion MRI and even resting state. So it's ongoing, and well, maybe in a few months we will have very nice results to show. And basically, all this data will be shared openly at one point. So. And I just end with this project. So this is, I think you are all aware of that, because it's a great project that has been funded very recently with Jeff, Pietro Gobri, and myself, where the aim is to pursue the efforts from the team of Jeff since 20 years with the foundation model of to decode cortical folding patterns. And I think here you understand well now that our data will be instrumental to help investigating really the impact of early brain development on this following pattern. And well, I stop here to have some time for questions. So well, just if we take a message, and well, thank you for your attention.